Hello everyone. Okay, so in this session I'm going to give a lecture on the moment error method. So basically in the previous class we have discussed in detail on the V2 method, and I have given some examples on how to use the V2 method to calculate the displacement and the rotation in the beam. So in this session we will learn in detail how the moment error method can also be used to calculate the displacement and the rotation in the beam. Okay, without further ado, let's discuss in detail on this particular method. Okay, so as an introduction, basically this method has been developed by the Charles E. Green in 1873. So the concept of this method is to determine the slope and deflection of the elastic curve due to the bending. So in other words, this particular method uses the deformation shape of a beam in order to calculate the slope and deflections in the beam. So this is one part of the process. So we will look in detail in the procedure of this particular method. The advantage is it deals with beams that subjected to series of loading or having different moment of inertia. In other words, this method is suitable to solve a beam that imposed by a combination of load. For instance, the point load combined with the UDL load, or any combination of load in a beam can be analyzed by using this moment error theorem. And if you have a different size of cross-section area along the beam, so this particular method also can be used. Okay, so different size will give different moment of inertia, or in other words, the I value. Okay, so the disadvantage of this method it can only be used to determine the angles or deviation between two tangents on the beam elastic curve. Okay, so basically they have two theorems that we need to learn based on this moment area method. The first theorem is about the angle, where we can use this particular first theorem to calculate the angle in a beam. Meanwhile, the second theorem is used to calculate the deviation or vertical displacement in the beam. Okay, so let's discuss in detail how this first theorem is established. Okay, so this first theorem, you can see that the equation is given by this theta BA equal to integration of m over EI. So m is referred to the moment, EI is a flexural rigidity, and we need to conduct integration process in order to calculate the value of rotation in the beam. Okay, so to understand how we can use this particular equation, we need to some explanation from this slide. Okay, so basically what you can see here, the change in slope between any 2 points on the elastic curve equals to the area of the MEI diagram between these 2 points. So basically this sentence can be explained by looking on this tree diagram. Okay, let's say we have a simply supported beam, okay, that loaded by the UDL, and let's consider the point A and point B along the beam here. Okay, so and this particular beam will be defect as what you can see in the third diagram here. So we call it this as elastic curve diagram for the beam. Okay, so by looking on this diagram, you can see that they have two tangent lines that have been drawn on this particular elastic curve. Okay, the first one is a tangent line A. We name it as a tan A. Another one is a tangent B. Okay, that we name it as a tan B here. Okay, so in between these two tangent lines, you can see that they have an angle that has been drawn from the tangent A to tangent B. So we name it this as theta BA. So basically this is a change in slope. Okay, so change in slope, and this particular change in slope can be calculated by using this MEI diagram. So what you can see that in this shaded area from A to B. So basically this A to B is represented, okay, the area from A to B for this curve is represented for the change in slope of theta BA in this particular diagram. Okay, so the notation is theta BA is referred to as the angle of the tangent at B measured with respect to the tangent at E. Okay, so the sign conventions, you may refer to the third sentence in this slide. So the angle is measured counterclockwise from tangent A to tangent B if the area of the MEI diagram is positive. For instance here, so this MEI diagram is positive. So the rotation of this angle is counterclockwise. So if clockwise, so the angle will move from the tangent B to tangent A. So we name it this as a theta AB. Okay. So one things that you need to take note here. So the theta BA is equal to theta AB. Okay. So if you draw the line, so the curved line for angle from B to A or A to B, so the value is equal. Okay, based on this expression. Okay, so let's move on the second theorem. Okay, so what you can see in the second theorem, we have x bar. Okay, so I'm going to explain in detail how to get this particular x bar. Okay, multiply with the integration of m over ei. So they have additional term in this equation when you compare with to the first theorem. So in the first theorem, this particular x bar did not exist. Okay. So to understand these equations, so we need to refer on this diagram. Okay. Let's look on the definition of the second theorem. Okay. So the vertical deviation of a tangent at a point A on the elastic curve with respect to the tangent extended from another point B equals the moment of the area under MEI diagram between the 2 points, which is referred to point A and the point B. So this moment is computed about point A at the point on the elastic curve where the deviation is to be determined. Okay, so I guess that most of you couldn't understand what is this sentence explains about. So we need to understand this sentence by looking on the diagram. Okay, let's say we have a same situation as a first theorem. Okay, basically this is the diagram that we have seen in the first theorem. We consider 2 points A and B. So this beam is loaded by the UDL. Okay, so this is an elastic curve diagram for the beam, or in other words, this is a deformation shape of a beam due to the load applied. So we have a same point A and B. So by drawing the tangent line A and the tangent line B, so you can see that we have one straight line. Okay, this is a straight line where from tangent that has been drawn from tangent B to the point A, and another one is from tangent A to the point B. So I can say that this is a vertical deviation, okay, for point A, and this is a vertical deviation for point B. So basically this vertical deviation can be defined as a distance between tangent line towards the deflected point. So what you can see here is this is tangent line. Okay, this is a deflected point. So when you want to draw the vertical deviation, you need to ensure that the vertical deviation must be drawn from tangent line towards the deflected point. So this is very crucial. So this definition is very important so that you can draw the correct vertical deviation for the specific point. Okay, so this vertical deviation basically can be calculated by using the MEI diagram. So where you can use this particular equation. Okay, let's say our range is A to B. So by looking on this diagram, so this is A to B. So this area of MEI diagram from A to B is represented for the vertical deviation for this tangent AB. Okay, so besides that, you can calculate the the vertical deviation for TBA, where in this case you can see that the TAB is not equal to the TBA. So the vertical deviation AB is not equal to the vertical deviation for the BA. Okay, so where this is opposite from the definition from the first theorem, where the theta BA is equal to theta AB. So this not for the theorem number 2. Okay, so I hope that you can note this particular difference between the first theorem and the second theorem. Okay, so okay, the x bar here is refer to the distance between the center of area. Okay, for instance, this is the area that we have considered for this particular limit a to b. So the x bar is measured from the center gravity of this area towards the point A. Okay, so let's say we wanted to calculate the vertical deviation for the TBA. Okay, so for this case, the distance must be considered from the point B. Okay, the point B towards the center gravity of area of this MEI diagram. So the easiest way to identify the value of x bar is by looking on the first alphabet in the vertical deviation symbol here, in the expression. Okay, so for instance here, A is come first than the B. So in this diagram, you can see that the x bar is measured from A to the center gravity of the area. If I want to calculate the vertical deviation for TBA, so we can see that in this expression, B is come first than the A. So the x bar can be calculated by measure the distance between B towards the center gravity of this cross-section area between the limit of A to B. So I hope that you can understand how to use this particular equation. Perhaps at the moment you couldn't understand how to use this equation. Maybe we can look on the examples later on. Okay, so basically in this slide is trying to explain about the procedure of analysis. Basically, they have 3 major steps, where the first step, you need to draw the MEI diagram. Okay, so we will discuss in detail how to draw the MEI diagram based on the example that we will discuss later on. Okay, so in this MEI diagram, basically you need to calculate the value of moment equation. So you need to carry out some of beam analysis that you have learned in the previous class, or in the previous knowledge that you have learned. Okay, and the second step, you need to draw the elastic curve diagram. So basically this elastic curve diagram is referred to the deflected shape of beam, or deformation shape of a beam due to the applied load. So you need to have a sense how to draw the deformation or deflection shape of a beam. So it's very important in this method. Okay, the third step, you need to apply a moment area theorem. So we have seen that they have two theorems, theorem 1 and theorem 2. Okay, sometimes we need to use a combination of both of these theorems to solve a certain problem. So you will see this in example. Okay, so I think that's it for this sessions. So in the next sessions, we will discuss on the example. So basically, they have 4 examples that we're gonna to discuss in detail on this moment area theorem. So thanks for listening.